Today, I'll talk about our work on compiling graph applications for GPUs with Graphite. This work was done jointly with my collaborators from CSAIL MIT and Adobe Research. In 2018, we first developed the Graphite domain-specific language and compiler to navigate the vast optimization space and graph applications required to get the best performance across variations in algorithms like data-driven versus topology-driven, and graph inputs like power law degree distribution and bounded degree distribution, among others. The way Graphite works is that the user can supply what to compute in an algorithm language and how to compute in a scheduling language. The specialized compiler then generates high-performance C++ code out of this. The user can then further tune the scheduling language input to better suit their particular graph input and algorithm. This works well for CPUs, but not all applications are well suited for CPUs. Some applications like PageRank, when running on social graphs, have massive amount of parallelism and regular access pattern and are better suited for running on GPUs. Applications like SSSP, when running on road graphs, are better suited for CPUs. What this currently means is that the developer now has to rewrite these implementations by hand in a language like CUDA. But just like CPUs, each input and algorithm requires different optimizations. In fact, the optimization space in GPUs is an order of magnitude larger than that of CPUs. Currently, there's a lack of a single framework that can generate the best code for both CPUs and GPUs from a common input. To solve this exact problem, we introduced the G2 compiler extensions to Graphite. G2 keeps the same algorithm language as that of Graphite. This means that the developers do not have to re-implement the algorithm from scratch. But G2 adds a new scheduling language that is tailored specifically for optimizations on GPUs. Here is a list of optimization choices that the G2 compiler presents to the user. The details of how each of these affect performance of the graph applications are detailed in our paper. On the right, I have shown the functions in the scheduling language that the user can call to tune these optimizations. This table shows all the available optimizations in G2 and other state-of-the-art graph framework for GPUs, Gunrock, GSwitch, and Subgraph. We can see that because of G2's rich scheduling language, we are able to generate an order of magnitude larger number of optimizations. The optimizations in the G2 compiler are divided into mid-end optimizations and back-end optimizations, based on whether they are common to both CPUs and GPUs or specific for GPUs. The mid-end is a series of analyses and transformation passes running on the algorithm input, parameterized by the scheduling language. This includes passes like dependence analysis for user-defined functions that automatically decides where to insert atomic synchronization based on the chosen load balance and direction of iteration. The GPU backend has analyses and transformations specific to the GPU. This includes analysis passes like liveness analysis that determine which data structures can reuse allocated memory. This is required for GPUs because unlike CPUs, the allocation and deallocation costs on GPUs are very high. Similarly, the GPU backend has transformation and lowering passes that convert entire while loops into single CUDA kernel, fusing the individual operations inside the while loop. This is required to eliminate the overhead of launching separate kernels when the number of vertices to be processed in each round are low. These passes are explained in detail in the full presentation. Finally, the GPU backend has a rich runtime library that has functions for load balancing, frontier and priority queue management, among others. Our paper also has a detailed evaluation of G2, comparing the execution time of its generated code with the other state-of-the-art graph processing frameworks. Of the 90 experiments that we run, G2 is fastest on 65 of the experiments. We also have a detailed breakdown of the performance gains from some of the new optimizations we added. G2 is able to achieve all of this with far fewer lines of code input than other frameworks. G2 is available open source on our website on the following URL under the MIT license. Please reach out to us if you have graph applications that you want to run faster on both CPUs and GPUs. Thank you.